Ladies and gentlemen, welcome back to another lesson in group theory. In this lesson, we'll be covering the proof of two propositions which we've already seen in lesson 5. If you haven't seen them, I strongly suggest you do, because they cover a very important yet natural group in group theory, which is called the symmetric group. This lesson is going to cover the proof of two particular propositions that are important and satisfying. The first covers a formula that concerns the conjugation of an element in the group Sn. So the conjugation of an element sigma is called tau sigma tau inverse, where tau is another permutation in the group Sn. The second proposition that we're going to cover is calculating the order of an element in Se. In other words, calculating the order of sigma. For sigma, any permutation in Se. Let's get started. The first proposition covers a formula we've already seen and used in lesson 5. The proposition goes as follows. Let sigma be the cycle of x1, x2, all the way to xm, and let tau be another permutation. So we have that the conjugation tau sigma tau inverse is equal to tau x1, tau x2, all the way to tau xm. It is as simple as that. To prove this proposition, we need to see where tau sigma tau inverse takes y to. So let us see the different cases. First of all, if y is not an element of tau x1, tau x2, all the way to tau xm, then we expect in our proof, because y is not in this cycle, then this permutation has to fix y. So we have tau sigma tau inverse of y has to be equal to y. We need to prove this. How do we prove it? So, since y is not equal to tau of xi for all I between 1 and m, so x1, x2, all the way to xm, if we apply tau inverse on both sides of the equation, so we compose tau inverse, and we have that tau inverse of y is not equal to tau inverse of tau of xi, and tau inverse of tau is just the identity, so we have that tau inverse of y is not equal to xi for all I between 1 and m. So again, we have this relation now. So because tau inverse of y does not appear in any of the x's in the cycle of sigma, that means sigma has to fix tau inverse of y. So tau sigma of tau inverse of y, so if we look at it as sigma applied on tau inverse of y, then this means that this is equal to tau of tau inverse of y, because like we said, sigma fixes tau inverse of y. So now we can just compute tau composed with tau inverse of y, and that is the identity, so it's just equal to y. Thus we've successfully proved that for any y that does not appear in the list of the cycle tau sigma tau inverse, then this permutation, the conjugation, will fix y. Suppose now that y does appear as one of the elements in the set. So suppose that y is equal to tau xi for some I between 1 and m. If we have that, then we calculate tau sigma tau inverse of y to be just replacing y by tau of xi to get tau sigma tau inverse of tau xi. And now we can compose these two together to get the identity permutation. So this is all just xi. So this is tau sigma of xi. And now we use the definition of sigma. So we go back and see that sigma sends each xi to xi plus 1. So example, x1 is sent to x2 by sigma. x2 is sent to x3. So xi is sent to xi plus 1. And this equals to tau of xi plus 1. And this agrees with the proposition or the claim that tau of x1 goes to tau of x2. So tau of xi goes to tau of xi plus 1. The last thing that we need to prove is that tau of xm goes all the way back to tau of x1. And this proof is direct. We just need to calculate what happens for tau of xm. So we need to say, okay, tau sigma tau inverse of tau of xm. And this again with the identity being tau of sigma of xm. And because sigma is the cycle that takes xm all the way back to x1, this is just equal to tau of x1. And this completes the proof of this proposition. Let us now move to the proposition that calculates the order of a permutation in Sn. Let sigma be in Sn. Then the order of sigma is the least common multiple of the lengths of the cycles in its composition. So to prove this proposition, we need to say that we know by the proposition that we've seen in the video, the lesson 5.1, we know, by the way, I recommend you to check the statement of the proposition and the proof of lesson 5.1 to understand really how any cycle can be decomposed into disjoint cycles. We know that sigma can be decomposed into disjoint cycles. So we're going to write sigma as a product of disjoint cycles, C1 to Ck, where Ci and Cj are distinct if I is not equal to j for all I and j between 1 and k. Ci and Cj are disjoint if I is not equal to j for all I and j in 1 to k. Now that we have sigma, we can take the lth exponent of sigma, so the lth power of sigma, but the lth power of sigma is equal to the lth power of C1 Ck. But because C1 and Ck are disjoint cycles, we know that disjoint cycles are commutative. And a nice property about commutativity is that we can distribute the exponent on all the individual components. So we have C1L all the way to CKL, because disjoint cycles are commutative. Note that each m cycle, so a cycle of length m, has an order m, as previously discussed in lesson 5. So note that an m cycle has order m. To recap, the order of an element is the smallest integer, such that if you take that element to the power of that integer, you get the identity. If sigma to the L is equal to the identity, then it is necessary that all the Ci's to the power L is equal to the identity for all I between 1 and k. Which makes sense because sigma is the product of all these Ci's. So if sigma to the power L is equal to the identity, then it is necessary that all of the products are equal to 1. Otherwise, we would have a contradiction. So this statement means or implies that the order of each Ci divides L, because we find that if we find a number in which we have Ci to that exponent gives the identity, then the order of Ci has to divide this number. So each Ci divides L. That means that the least common multiple of each Ci also divides L. The least common multiple of the order of C1, the order of C2, all the way to the order of Ck divides L. And now we see that since the least common multiple of the orders divides L, then the order has to divide LCM. But we want to know if the LCM itself, if we take sigma to the power of the LCM, are we going to get back the identity? Because if not, then the order has to be bigger than the LCM. So let us check that. So we have that sigma to the power of LCM, C1, C2, all the way to Ck, is equal, in fact, to Ci, so all the Ci's, C1 to the power LCM, C2 to the power of the LCM, all the way to Ck to the power of the LCM. But because the LCM is a multiple of the order of each of the Ci's, we must have that all of these Ci's individually will give the identity element. This is identity, and this, and also that. So the product of all these identities is going to give us the identity element, thus making the LCM, in fact, the order of sigma. So the order of sigma is equal to the LCM of the order of C1, the order of C2, all the way to the order of Ck. And this completes the proof of this proposition. If you enjoyed the proof of these two propositions, please like, subscribe, and I will be giving more lessons on group theory where we will be discussing special types of groups and homomorphisms, isomorphisms, quotient groups, normal subgroups, and much more in future lessons. Have a nice day, and I'll see you on the next time.